Welcome everybody to the second lecture in electromagnetic waves, and today we're going to start talking about magnetic static field or magnetostatic and introducing the fundamentals of magnetostatic. Before we start, I have a homework for you, which is to just review the vector algebra so that you are up to speed on using them, because we're going to use them frequently in magnetostatic part and in electromagnetic waves as well. So how this topic, magnetic field, was sort of like introduced to the science society. We know that static electric field is due to charge at rest. So unmoving charge, the vector quantities for electrostatic field is electric field intensity E and electric displacement field D, or electric flux density, which accounts for the effect of polarization in materials that is not free space or like air. The electrostatic model does have like two postulates, or like two major postulates or fundamental laws that governs the topic. Number one is the divergence of D equal the rho, which is volumetric charge density, and the second postulate is that the curl of E equals 0, which means that the electric field is conservative, or the potential difference between a point and itself over any closed path equals 0. And also the relationship between electric field intensity and electric flux density is the constant epsilon for linear and isotropic media. So this was studied early on. Then the scientists came across a different scenario, which is when this charge is moving. So what is the laws that would govern like this situation, a moving charge, a moving electric charge? And actually they started in two phases. The first phase is the case of like a steady state motion, so moving at a constant speed. The second situation is when they studied the motion at a varying frequency, which is the second case is the case of electromagnetic waves. The first case, the steady state motion or steady state electric current, because when a charge is moving at a constant speed, this is like a steady state current. This is the case of static magnetic field, and this is the case that we're going to start with in this part of the course. So the observation that they found about electrostatic field was the case of a charge moving in a field like close to a magnet or something like that. So the observation started by observing the force, very similar to the electrostatic case. When we have a charge close to another charge, there is a force between of them, and this is Coulomb's law of force, and from this observation they introduced the electrostatic field. Here we have another case when we have a charge moving in magnetic field. Let us say a magnetic field caused by a magnet, because in the nature there is some magnet. They found that the force can't be explained with the electric force, so they said there must be another type of force related to this case, which is the magnetic force. And they tried to put a mathematical model for the observation, and the mathematical model that they came up with is that this force, this magnetic force, is proportional to the charge quantity of the particle. It is proportional to its velocity of motion. It's proportional to the amount of the magnetic field as well. and its direction is perpendicular to both of them, perpendicular to the velocity and perpendicular to the magnetic field direction. So the characteristic of the magnetic force can be described from this situation here, where we have, like, let us assume that we have a charge at rest, and then we applied a perpendicular electric and magnetic fields. The electric field will insert some force on the charge Q that's causing the charge to move along this line, which is perpendicular to the magnetic field. Because of the motion of the charge, the magnetic field will exert another force, another component of force on the moving charge, and this component is in the direction of V, velocity, cross B, the direction of the magnetic field, which is outside of this screen. So the charge will be moving along, if the charge is positive, it will be moving along the direction of the electric field, and this will cause it to be affected by another force, the magnetic force, that is causing the charge to change its direction with a component in the direction out of the screen, and this is called the Lorentz force law. Some people say this is the fifth Maxwell's equation, but again, this is one of the major laws that is governing the electromagnetic field or topic of science. So the definition of magnetic flux density is something similar to how we define the electric field. When we have like a magnetic field, this will cause some, when we have electric field, this will cause some electric force, and the relationship between the electric force and the electric field is the quantity of Q. Similarly, when we have magnetic force, this is related to both the velocity of motion of the charge Q and the direction of what we define or call as the magnetic flux density. Also, the force is related to the direction of the two quantities, the velocity and the flux density, with the cross product. So the force, the magnetic force, is proportional to Q, proportional to the speed of motion of the electric charge, proportional to the flux density, and proportional to sine the angle between the two vectors. So if we have a charge that is moving in the same direction as the magnetic flux field, there will be no force here because sine theta will equal 0. So the cross product of two vectors in the same direction equals 0. If we have this charge moving in a direction that is perpendicular to the direction of the magnetic field, there will be magnetic force that is perpendicular to both of them, because this is a definition of the cross product. So you put your hands, your fingers of the right hand along the direction of V, and then rotate your fingers towards the direction of B. This will give you the direction of the force. In this case, the direction of the force is out of the screen. If the charge does have like an angle with the direction of the magnetic field, there will be no change in the component along the direction of the magnetic field, but the component along the direction perpendicular to the magnetic field will cause a component of force that is perpendicular to the screen. So here, like, we must use the vector decomposition to know the component that is parallel to the magnetic field, and this will cause no force, and the component perpendicular to the magnetic field, and this will cause a component of force. The magnetic flux density does have the unit of Newton divided by Ampere dot meter, and this unit is called Tesla or Weber per meter square. So the magnetic flux density does have the units of Tesla, which is also called Weber per meter square, or in the fundamental units, it's Newton divided by Ampere dot meter. So here, because the magnetic force is always perpendicular to the direction of motion, the path of the particle is circular. So let us assume we start at position 1 here. So we have magnetic field that's going out of the screen, and we have a charge that is moving along this direction. At the beginning of observation, the charge, positive charge, is moving in this direction. So there will be a force that is going from, so like you put your right hand fingers along V and you move your fingers towards the direction of the magnetic field. So the direction of the magnetic field is outside of the screen. So you move towards the direction of outside of the screen, and you will get the force to be in that direction. So the force is going in that direction, perpendicular to both of them. So the force must be in the plane of the screen. It's perpendicular to V, so it is either up or down. It's perpendicular to this one, which is out of the screen. And to know if it is the direction, you use the right hand like rule, and you will find the force going in that direction. So the moving charge will start to bend its direction a little bit. So it will come to this point. Again, you do the application of the right hand rule, you will find the force always going like in the direction towards a center of something. So this will cause the charge to move in like a circular path, and with some analytical studies and derivation, we can find the radius of this circular path, and this radius equal the mass of the charge multiplied by its velocity divided by the amount of charge and the magnetic flux density. So if a particle with velocity that is inclined to the direction of the magnetic field, its component along the direction of the magnetic field will not change because there is no force caused by this component, but the component, because of the component of velocity perpendicular to the magnetic field, will be like perpendicular to the screen, and this will cause, like if we start at this point with a charge that's moving in that direction like a straight line, and once it goes into the magnetic field lines, its motion will start to be helical, like a helix. Why? Because some component is constant because of this component of velocity. It will not change, it's parallel to the magnetic field. But there is another component that is perpendicular to the magnetic field, and this will cause some circular motion. So we'll have two kinds of motions, circular motions and like longitudinal motions, and instead of moving in a circle, we'll start moving in a helix. how large this helix is related to this r, and how frequent it is related to this velocity. So if the longitudinal velocity is the dominant, we'll have this is like a wide helix. If the longitudinal velocity is small, we'll have very tight helix, so on and so forth. And this kind of the physics of motion of charged particle in magnetic field does have some application. One of them is the mass spectrometer. So if we have some material and we can ionize this material, and this material is composed of multiple particles, so and then we just accelerate those particles and throw them in a perpendicular magnetic field. Each ionized item will have its own circular path with radius that is related to the ratio. All of them are at the same speed. All of them are exposed to the same magnetic field. So the ratio of m over q, mass to charge, will cause different radius of motion. And if we can have a collector here that counts the number of ions of this type, and another collector here that counts the number of ions of this type, we can like calculate the number of ions of each type, and we can do some sort of like material analysis, and this is called mass spectrometer. So here we're gonna watch a video. Let me see how to. So let us see like a video that visualize this item.
Motion of a charged particle in a magnetic field. Consider a positive charge Q moving in a uniform magnetic field B. It will experience a force called Lorentz force, given by F is equal to Q into V cross B. This force changes the direction of motion of the charged particle. Let the angle between the velocity of the charged particle and
use
the
your right
magnetic
hand
field be
to
theta.
calculate or to find the direction
The
of
direction
the
of
force,
force experienced
so that you
by
can
the
also
particle
like benefit
is given
from
by the right hand
this
rule,
video.
which
So
states
apply
that
your
if you curl the
own,
fingers of your right hand from V to
like
B,
exercise so
then
that
the
you
thumb
can
gives the
learn how to
direction
use
of the
it on
force.
your own.
Thus, the force is perpendicular to the plane containing V and B and acts in the upward direction. If a negative charge moves instead of positive, then, according to the right-hand rule, the force will act in downward direction, and the particle gets deflected in the downward direction. Let us study different possibilities. Case 1. The positive charge Q is at rest in the magnetic field B. It remains at rest as the magnetic field does not exert any force on a stationary charged particle. Case 2. The positive charge moves parallel or antiparallel to the magnetic field. It continues to move along the same line with the same velocity in the same direction, since the force experienced is again zero. Case 3. The charged particle moves perpendicular to the direction of magnetic field. It experiences a force in a direction perpendicular to the plane containing V and B. This force provides the centripetal force and makes the charged particle move along a circular path of radius r equal to mv by qb. We now consider three different charged particles: proton, deuteron and alpha particle moving with the same velocity v in the same direction in the given uniform field. As soon as the magnetic field is applied, all three of them start moving in a circular path. Since the radius of the circular path depends on the charge and mass of the particle, it'll be different for different particles. Next, we consider an electron and a positron moving with the same speed in the same direction. On applying the field, they traverse the circular path in opposite direction due to opposite charges. The charged particle moves at an angle theta to the magnetic field. The velocity v can be resolved into two components: v sin theta perpendicular to the field and v cos theta parallel to the magnetic field. Due to the perpendicular component of the velocity, a force F acts perpendicular to B and to v sin theta. This force causes the charged particle to move along the circular path. Due to the parallel component of the velocity, no force acts on the particle and it continues to move parallel to the magnetic field along a straight line with the velocity v cos theta. The combined effect of linear motion along the field and circular motion in a plane perpendicular to the field is helical motion, with the axis of the helix along the magnetic field. A helix is characterized by its pitch and the radius. Pitch is the linear distance covered by the particle along the magnetic field in one complete cycle. As the angle theta between the velocity and the magnetic field increases, the radius increases as it depends on v sin theta, and the pitch decreases as it depends on v cos theta.
So one thing to remember here is that this or to pay attention to is that the magnetic force doesn't exert work on the charge. So it doesn't change its amount of power or kinetic energy or speed. It just changes the direction of motion. While in the case of electric force, it exerts work on the charge. So a charge at rest can be accelerated with electric field, but a moving charge can't change its speed because of the application of a magnetic field. All what happens is a change of the direction of motion. So this is one major difference between electric force and magnetic force. Another application that's used in physics for this phenomena of magnetic force is called the Hall effect. So let us consider this sort of circuit. So we have here some DC voltage source that is applied on a sheet of metal. Because of this applied voltage, there will be current in this direction, which means the free electrons are moving in that direction. So when we have it's a steady state voltage source, so we have a steady state current on the sheet of metal, which means that there is a stream of electrons moving with a constant velocity in that direction. So now let us apply a magnetic field in that direction, in the normal to the sheet in the up direction. So now we have a velocity in that direction. We have a field, magnetic field up. So applying the right hand rule, there will be a force in the left direction. Why? Because this is a negative charge. So applying the right hand rules, then like we have in z direction velocity, in the up direction we have field, so the thumb of our right hand will point to the right, but because this is a negative charge, the force will be to the left, which means that the stream of charges moving in that direction will be pushed to the left, accumulating and putting more density of electrons on the left side, and when the electron moves out of its position, it will leave some positive charge. So there will be more holes or positive charge accumulated on the right side and electrons accumulated on the left side, causing electric field that is pointing in that direction from right to left. Electric field pointing from right to left will cause some force trying to bring the charges from left to right. So this is happening very, very fast, and we reach a certain equilibrium status where the electric force that's trying to pull the electrons to the right equal to the magnetic force that is pushing the electrons to the left. Under this condition, we have equilibrium. If we measure the voltage difference between the right side and the left side, we'll have some voltage because of this Hall effect, and this voltage is the potential difference at equilibrium. From this voltage you can calculate we can know the charge density in this material. We can know some physical properties about the material, and this is called the Hall effect. Now we come to the point of how would we generate magnetic field. As I said, the magnetic field is generated by a steady state moving charge or steady state current. So if we have a steady state current flowing in a straight wire, this wire will generate magnetic field that follows this shown rule here. If you put your thumb along the direction of current flowing in the wire and just bend your right hand fingers, the right hand fingers will point to the direction of rotation of magnetic field. Remember that magnetic field is closed lines or circulating. The magnetic field is a circulating field or closed line fields. And if we put this wire in this shape and we bring some paper sheet or something, and we put some iron powder or like steel powder, very small particles of iron on this sheet, and we just check them, they will be organized in circles along the direction which is the shape of the magnetic field generated by this current. We can also find the direction of the magnetic field using the needle of compass. So the needle will be oriented along the direction of the magnetic field. So if we have this wire carrying current and we have like a number of compasses, the compasses will point in the directions as shown here in this sketch. Now we're going to start studying the magnetostatic field in free space. So for charges in motion, it will constitute current. Current will create magnetic field around. So what we are studying here is the steady state current. For static magnetic fields, we have two postulates, two basic laws that governs the magnetic field. And those postulates are not driven from like other rules. It's just a mathematical model for the observation. Number one, divergence of B equals 0. And we're going to understand the meaning of this one very shortly, but it is saying that there is no isolated source of magnetic field, or in other words, because it's related to the divergence, the field lines of the magnetic field are closed lines. It's different than the electric field, which is open lines, or the line goes from one charge to infinity or from one charge to a charge of opposite polarity. Here, for magnetic field, the generated field lines are closed lines. Number two is the curl of P is related to mu naught J. J is the volumetric charge density. So here we know that the divergence of a curl equals 0. This is a null identity of the vector algebra. For any vector, if we calculate the curl and then calculate the divergence of the curl, will have 0. So if we have divergence of both sides, will be divergence of curl of B equal mu naught divergence of J, and this equals 0 because of the null identity. So divergence of J equals 0, which means that this is the case of steady state current. Why? Because the flow, again, the current in and the current out of any volume are equal to one another. There is no difference, so it is a sign of steady state current. Later on, we're going to show that the relationship between the magnetic flux density and magnetic field intensity is a constant mu. It's called the permeability, and permeability in free space equal 4 pi multiplied by 10 to the power minus 7, and we're gonna talk about this later on. As I said, the divergence of B means that no magnetic analogous to electric charge. So there is nothing called like sort of like magnetic charge or something equivalent to magnetic charge. So if we have divergence of B equals 0, so we can say that like the integral form of it, B dot ds equals 0 over any closed surface, and this is called the law of conservation of magnetic flux, which means that magnetic flux lines always are closed lines. So here, if we looked for a permanent magnet, all of us know about a magnetic bar. So if we have like a magnetic bar and we split it into two halves, we will have two magnetic bars. If each bar does have a north side and south side. If we keep splitting them, each part that we split will also have two poles, south pole and north pole, all the time. Like no matter how small you make it, you will find a north pole and south pole, and this is just like confirming what we're saying, that the magnetic source is coming in pair, and the charge will be always like in closed loop. The charges are going out of the north pole, going in to the south pole. This is the direction of the magnetic field associated with a permanent magnet or any magnet. no matter how small this magnet is, no matter how many times you split it into smaller pieces, you will always find this shape: north pole, south pole, and the electric fields are closed loops around them. Okay, having said that, let us look at some of the things that we usually see on the refrigerator. We have those refrigerator cards. Those refrigerator cards, like from one side, the black side, they can be attached to like a metallic surface. If we just flip them and try to attach them, they will not attach to the metallic surface. So it looks like in this case we have a magnetic field from the back side, no magnetic field on the front side. So how is this goes with what we're just saying, that we always have the magnetic sources in pairs, north pole and south pole. So what happens in this case? So actually this is called like a Hall patch array. Hall patch array is sort of like an engineered body or like engineered structure of magnetic material. So if we have those kind of U-shaped like magnets, so we have north, south, when we arrange them like this, the field will be confined in one direction. So if we have some magnetic material and we arrange the magnetic material this way, so we have like this is the north pole of this triangle, this is the north pole in this triangle, this is the north pole. So we have a rotating north pole. This will generate the magnetic field, or like the total or the summed up magnetic field will be concentrated in one side with cancelled out or very weak magnetic field on the other side. And that's why from the back side it can be attached to a metal, from the front side it can't be attached to a metal. So it's sort of like an engineered structure of magnetic material such that the magnetic field is concentrated in one side and cancelled out in the other side. One also nice thing about the magnetic field is that we say that the magnetic field goes out of the north pole and goes into the south pole. Like now let us look for the geography of Earth. What we call the north pole is actually the south pole, the south magnetic pole of the Earth. So the geography north is actually physically the south pole of the magnetic field of the Earth. Why? Because the field direction is this way, which means when you have a compass, the compass is pointing out to the north side, which means the magnetic field is going to this side, which means the magnetic field is going in. So this is magnetically or physically is the south pole, but geographically we are saying this is the north pole or the north side. I think this is how things started, and they didn't change because they are talking about the north direction, but actually this north direction is the south pole of the equivalent magnet of Earth. So this is just like a piece of funny information about a magnetic field. So now, how would we calculate the magnetic field generated by certain source of current? The major rule here is called Ampere's law. So what does Ampere's law states? So what is Ampere's law is stating? Ampere's law is stating that the current through a surface divided by closed path is related to the magnetic field along this path. So we know that any closed contour defines an open surface, any closed surface defines certain volume. So the circulation of the magnetic flux, so this is Ampere's law, meaning the circulation of the magnetic flux in free space around any closed path. So if we have any closed path of any shape, like this arbitrary shape here, the circulation, which is B dot dl along this path, equal mu naught multiplied by the total current flowing through this open surface. And the current here must be, of course, the normal component, because this is the definition of current flow outside of this surface. And here we need to remember one thing, is the open surface does have two sides. Are we talking about the top side, which is pointing out of the screen, or the bottom side that's pointing in the screen? So which one is intended in this Ampere's law? So it is the one that follows the right hand side rule. So here, if you put your fingers of the right hand along the direction of rotation of the contour, you will find that your thumb is pointing out of the screen, and this means that we are talking about the top surface of this like open surface, the top side of this surface. We can talk about the bottom side of this surface, but in this case we'll be pointing out like we need to have the rotation like clockwise. Okay, so what Ampere's law is saying, that B dot dl along any contour equal the total current flowing outside of this open surface defined by the contour, and top side or bottom side is defined by the direction of rotation of the contour, and there is a constant mu naught in the right side, or multiplied by the current. So as we said with Gauss's law, Ampere's law is always valid, but it is useful only in solving a problem when we have symmetry. Very similar to the case of Gauss's law in electrostatic field. So we can use Ampere's law to find magnetic field around straight wire. Why? Because we have symmetry. So if we have like a very long straight wire, we have two symmetries. We have symmetries in phi, we have symmetries in z, so that we know the magnetic field in this case must be in this plane, must be in the horizontal plane, and because it is must be like a closed line, so we can say that because of the symmetry, the physical symmetry, the magnetic field must be in circles. So we can use Ampere's law to find this value. So what Ampere's law is stating mathematically is B dot dl over any closed contour equal mu naught I, where I is the component of the current that is perpendicular to the surface defined by the contour. So let us assume that we have this wire, and this wire is carrying current. Of course, here we're talking about steady state current. We can apply Ampere's law to find the field. We know that the field must be circular because of the symmetry. We have like a phi symmetry and we have z symmetry, so the field must be circular. So if we choose our contour to be a circle centered with the axis of this wire, we can say that B dot dl equal B multiplied by 2 by r, and this will equal mu naught I, and we found the magnetic field quantity using Ampere's law. If we choose the contour to be a square, Ampere's law is valid. B dot dl along this contour will equal mu naught I, but we can't find the magnetic field using this way. Why? Because the magnetic field is changing along this contour, we don't know like how it is changing, we don't know like the format of the change, we just know collectively the integration on the left equal mu naught I, but we can't find the field. So this is similar to, okay, we have like a group of 10 students and we say that, okay, the total money with this group equal like 1,000 TL. Okay, you can't tell this way what is the amount of money with each student. But if you say that those students does have equal amounts of money and the total money they have equal 1,000 TL, you can calculate the amount of money with everyone, with each one of them. So this is very similar to the case here. When we have symmetry, this integration will be a multiplication. B multiplied by the length. So we can find B. But if we choose this one, we don't know like how the field is varying. So we can't find the magnetic field with this choice of the contour. So the choice of the contour is very important, and this is why we're saying Ampere's law is always valid, but it is not always useful in solving the problem. To be useful in solving the problem, the contour must be symmetric, where we have magnetic field constant along this contour. If we choose a contour that is not fully enclosing the current, Ampere's law also is valid. B dot dl along this contour equals the amount of current enclosed by this contour, which will be part of this I. Again, if we don't have a symmetric field on this contour, or we don't know the relationship between B or the form of B along this contour, it would be like not possible to use Ampere's law to solve the problem. And if we use H, we'll just omit mu. So H dot dl over a closed contour equal the total current enclosing the total current enclosed by the contour. So now we want to use Ampere's law to solve this problem. In this example, we want to find the magnetic field everywhere. And when I say everywhere, you must be able to like define how many regions do we have. So here actually we have 4 different regions: inside the inner conductor, between the 2 conductors, inside the outer conductor, outside of the 2 conductors. So we have 1, 2, 3, 4 regions, and we need to find the magnetic field in each of those 4 regions. So let us start. We'll do region number 2 because it's the easiest, and you're gonna know why it is the easiest right now. So we have region number 1. Let me do that. Region number 1, region number 2, region number 3, region number 4. So we assume that the current is uniformly distributed across the cross section. So if the current is I, so J equal I divided by A square on this one. Because of symmetry, this is a circular shape, so there is a phi symmetry. It is very long, so there is a Z symmetry. The field lines must be circular, and just applying H dot dl or B dot dl, it will be H multiplied by 2 pi rho, and the total current enclosed is I. So in region number 2, the field equal I divided by 2 pi rho, and we can find the direction. If the current is going in the screen using the right hand side, so the magnetic field will be circulating clockwise. if I is going out of the screen, the magnetic field will be circulating in the other direction, counterclockwise. So now go to region number 4, because it's the second easiest one. So again, because of the symmetry, the field must be in a circular shape, and we need to calculate the total current enclosed by this circle, and we'll find here the current is going in, the current is going out. It's the same current, so the total current enclosed equals 0, so there is no field in region number 4. So like this kind of coaxial structure is shielding the magnetic field from going outside. Okay, now we'll start to do like more difficult one, which is region number 1. So again, we have uniformly distributed current. So again, there is a symmetry in phi, there is a symmetry in z. So H dot dl will equal H multiplied by 2 pi rho. Now the issue is how to calculate the current enclosed by this path. It's by proportionality or by calculating the the current density. Current density is I divided by pi a square, and this area is by rho square. So the current enclosed will be I multiplied by rho square divided by a square. So the field, again, it will be circular in the phi direction, and equal I multiplied by rho divided by 2 pi a square. If we go for region number 3, which is, in my opinion, the most difficult, the most problematic in calculating, we'll do the same thing. The field is circulating in the phi direction. It's equal to 2 pi rho multiplied by h, and it's equal the current I minus some part of the current flowing on the outer conductor. So what is the current density? This is where most of the people do mistakes. The current density on the outer conductor equal I divided by the area, and the area here equal by c square minus b square. So we have c square minus b square. What is the current flowing in this shell? It's equal by multiplied by rho square minus b square. So the current enclosed by this in the outer conductor equal I multiplied by rho square minus b square divided by c square minus b square. And don't forget this component, which is I. And if we're taking this, the inner direction is the positive direction, then the outer current is in the negative direction. So this sign is important. Remember to include the inner conductor current is important, and this way of calculating the density then multiplied by the correct cross-section area is very important, and we'll have the H equals this quantity. So there is some manipulation and we can find the equation. And if we just draw at the center, we would have no current, so no fields. The field will grow linearly, then it will like decrease with a parabolic decrease, another decrease with a parabolic decrease till it reaches 0 here, and outside it's always 0. So this is like very useful to solve this example and understand how to do its steps correctly. We have some other components like a solenoid. So a solenoid is sort of like a helical shape for the current. So it's something like a coil, and this shape is called solenoid. So it's a helical shape along a longitudinal core. So how would we solve here? So first we start to look into like the shape of the field. So we have the current flowing this way. So each component, so the current, when the current is flowing in a circle, the field will be along the direction of the sum, using also the right hand rule. So the current is flowing the way that is shown here. And this loop is very large. So if we have like this is infinity, this loop is actually going very far like this. So there is no, like, or the field very close to the solenoid area is very low, and the field is concentrated here inside the core of the solenoid. So if we take the path this way, so we take a path like this one, if you look into this cross section, you will find that we have some currents. Here's the currents going outside of the screen. So here we have the magnetic fields line horizontal, and this is the other side of the solenoid. So the current goes out, the current goes in, and we choose our rectangular path this way. We know the fields going this way, it's a horizontal direction. We know that there is no field at 3 because the loop is closed very far, because it's a long enough solenoid, so we can neglect the fields here. B and dot dl here are perpendicular on 2 and 4, so what is left is just the flux, or like B dot dl on this arm. On arm number 2 and arm number 4, B dot dl equals 0 because B and dl are perpendicular. On arm number 3, B equals 0, it's negligible, like just outside the solenoid. So the only contribution is coming from this side, which is B multiplied by delta L. Okay, so what is the current enclosed by this loop? It's equal to this current I multiplied by the number of turns into this rectangle, which is N, the total number, divided by L, which is the density. So it is the density. If we multiply this number of turns with current I, it will give us the amount. So N is the number of turns in this section. If we divide it by L, this will give us the density. So N is the number of turns per meter multiplied by I multiplied by mu naught. This is the B, the magnetic flux density. So N is the turn density, number of turns per meter, and this is how we find the value of the magnetic field inside the solenoid. Another example is toroid. So the toroid is sort of like, also it's some sort of a coil, but it is wrapped on a circular core. So this is some sort of like a donut shape or Smith shape, and we have some sort of like a winding around it. So the winding or the coil around it is making like turn, going out, going in, out, in, out, in, out, in. So the cross section of this shape might be a rectangle, might be a circular. Here it is a circular, the cross section is circular, and the core shape is circular. Sometimes we might have the core cross section is a square, but the path is circular. So now let us look here. Do we have any kind of symmetry? And the answer will be yes. The symmetry is in the phi direction. Because of this structure, we must expect the magnetic field to be circulating in the phi direction. And it depends on the current direction here, if it's clockwise or anti-clockwise. Here the current is going out from the inner side, in from the outer side, so the magnetic field will be rotating against the right hand side in the direction of the current, so the magnetic field is rotating counterclockwise. So now we need to find the solution for this magnetic field inside the toroid. So here, as we said, the magnetic field is in the phi direction. So H dot dl equal H multiplied by 2 by rho. And what is the total current enclosed? It's the number of turns of those, the total number of turns of the toroid multiplied by the current, because all the currents are penetrating this contour in one direction, so it's in I. So H as a function of phi equal Ni divided by 2 by rho. If we try to calculate the field in this region, again because of the phi symmetry, if we just draw the contour here, we'll find that the magnetic field equals 0 because there is no current enclosing. If we go outside of the toroid, also we'll find that the magnetic field equals 0 because the total current enclosed equal Ni minus Ni. So the total current enclosed also is 0. So the field is confined inside the core of the toroid. Another topic that is related to the magnetic field and current flowing in wires is the force between current carrying wires. So if we have a current carrying wire in this direction, we know that the magnetic field will be in the direction perpendicular to the current, and putting our thumb along the direction of current, our fingers will show the direction of rotation of the magnetic field. So if we have a current carrying wire exposed to a magnetic field, if the magnetic field is making an angle, like this case, angle theta with the current, we need to calculate the force. So current flowing in this direction is equivalent to positive charge moving in that direction. So this is the direction of V, and this is the direction of B. So the force will follow V cross B direction. So V cross B direction. So the force will be in the direction, in this case, in the direction out of the screen. And this force will equal current multiplied by length multiplied by B sine theta. Theta is the angle in this direction. Theta is the angle, direction of current to the direction of the magnetic field. So this is theta. Okay, what would happen if we have two current carrying wires next to one another? So like if we have F1 in this direction, sorry, I1 in this direction, I2 in this direction, what would be the force between them? So the current here, it is in this direction, it will generate field around it, and this field can be defined by putting our thumb along the direction of the current, and we can like the fingers will be rotating to the direction of the magnetic field. So if the I1 will generate a field that is going in the screen at the position of I2. and I2 will be generating field that's going out of the screen at I1. So the force F21 is the force on number 2 caused by current number 1. So the field B1 equals this quantity. I2L is the distance between the lines. This will give us the force. So the force here, ILB sine theta. Sine theta in this case is 90. F2 is the force affecting current 2. 1 because of field generated by current 1. Field generated by current 1 equals this quantity. So I2L multiplied by B1 equals this quantity, which equal mu naught I1 I2 divided by 2 by the separation between the lines multiplied by their length. So if the two currents are in the same direction, the force, so I2 cross, this is going inside, so I2 cross, so the force here will go in, the force here will go in also, so those are attracting. If we go here, for this case, the currents are of opposite direction, so current 1 will generate the same field, which is inside the screen, but now also I2 is generating current into like the screen. So F1 will go out. F1 is the force on 1 caused by 2, which is F12 will go out. F21 will go out also, so they are sort of like repelling from one another. So when they are in the same direction, we have attractive force. When they are in opposite direction, we have repulsive force. And I want you to think about this case. When the currents are perpendicular to one another, so we have one current carrying wire going up, one current carrying wire going out. What will be the force style between them? You need to think about that. And here I'm just showing the same problem, this problem in like a more illustrative way, so that students can relate things in 3D easier. And here we are reaching the end of the lecture, where I just summarize the learning objectives of this lecture. I suggest that at the end of each lecture, the student look into this list and make sure that they learned the different points mentioned here. Thanks everybody, and meet you in the discussion session.